What's up, geeks, and welcome to the channel. It's the holidays, and you plan to take the next few days off to visit Paris, along with all of its main sites and attractions. Now, once there, you could waste a lot of time walking in circles, not even able to find the Eiffel Tower, or you could hire a local guide who is going to show you every attraction and tell you a lot of exciting stories. Okay, cool, but what does this have to do with today's video? Well, imagine you have a graph, and you want to traverse or iterate over the elements of this graph. However, you don't know, or rather, you don't want to expose the underlying implementation of this graph. Maybe this graph is a binary search tree or a red-black tree. Why care? Just like the guide doesn't really know who you are, but still is able to help you. All you want is to traverse the elements of this graph, in a depth-first search manner, let's say. Or in our example, all we want is to visit these particular sites that we find interesting. And to do that, the guide we hired will tailor the tour according to our liking. Or similarly, the iterator will visit the elements of the graph according to the algorithm we picked, and regardless of the actual underlying implementation of this graph. So, the Iterator Design Pattern is a behavioral design pattern which main idea is to extract the traversal behavior of a collection into a separate object called an iterator. This iterator object, on top of providing a way to traverse the elements of a collection without exposing its underlying representation, encapsulates all of the traversal details, such as the current position and how many elements are left till the end. Because of this, several iterators can go through the same collection at the same time, independently of one another. Now, if you have been watching our videos, you should be familiar with the example we are about to implement using the iterator pattern. This example will consist of two classes, the depth-first iterator and the breadth-first iterator classes you can see in front of you. Now, I'm not going to dive in the details of their implementation, as both of them were already covered in previous videos, and because I want the iterator pattern itself to be the main focus of the video, not the traversal algorithms. All I did here was kind of adapted these implementations to meet the structure of an iterator. Okay, the last missing piece is the interface. All iterators must implement the same interface. This makes the client code compatible with any collection type or any traversal algorithm. If you want to introduce a new way of traversal, you just create a new iterator class. Usually, iterators must at least provide one primary method for fetching the elements of the given collection. The client can keep running this method until it returns null, which means that the iterator has traversed all of the elements. Now, to test our code, all we have to do is create a bunch of vertices, assign their corresponding neighbors, then pick the iterator we want to use and invoke the methods we just implemented. When we run this piece of code, you can see that the output we obtain is a depth-first search traversal as expected. Let's go ahead now and take a look at the structure or class diagram of the iterator design pattern while relating it to the graph traversal example we just implemented. The first thing you may have noticed is the iterator interface. The iterator interface declares the operations required for traversing a given collection, like fetching the next available element or retrieving the current one, etc. Next are the concrete iterators, which were represented by the depth-first iterator and the breadth-first iterator classes in our previous example. Concrete iterators implement specific algorithms for traversing a given collection. The iterator object should track the traversal progress on its own. This allows several iterators to traverse the same collection independently of each other. Okay, the remaining pieces of this diagram are the collection interface and the concrete collections. And you may be thinking that in the traversal example we implemented, we didn't have matching classes for these. And you are right. You see, usually clients don't create iterators on their own like we did, but instead retrieve them from collections. This way we make sure that the iterator we are using is compatible with that particular collection. So what we should have had is a tree interface, let's say, that is implemented by a binary search tree class and a red-black tree class. The tree here is the collection interface, and the binary search tree and red-black tree classes are the concrete collections. The collection interface declares one or multiple methods for getting iterators that are compatible with the collection in question. whereas the concrete collections will return new instances of the particular concrete iterator class each time the client requests one. Now, what clients do is work with both collections and iterators via their interfaces only. This way, they aren't coupled to concrete classes, allowing them to use various collections and iterators with the same code they have. So, to sum everything up, the Iterator Design Pattern allows you to traverse the elements of a collection without exposing its underlying representation. Additionally, it encapsulates the details of a complex data structure and exposes to the client several simple methods to access the collection elements. Also, on top of reducing traversal code duplication, by following the iterator pattern, you will be applying the single responsibility and the open-closed principles because each iteration algorithm is extracted in a separate class, and you now have the ability to introduce new iterators without modifying the existing ones. So, that's it for this video. I hope it was helpful. Thank you guys for watching, take care, and I will see you in the next one.